That is a seriously big machine. The Large Hadron Collider, or LHC for short, is one of the largest machines ever built. Thousands of scientists and engineers involved, billions of dollars. When it's running, it can use as much power as a good-sized city. What it does is accelerate particles called protons to very nearly the speed of light, around a 27-kilometer underground loop. Well, actually, there are two beams of protons racing in opposite directions that can be brought together so they can collide. Now, everyone loves smashing things together. But with all the time and effort that has gone into the LHC, there must be a really good reason for building a machine that does that. And there is. It just takes a while to explain. But if you can understand the reason for building this giant machine, there's a very good chance you'll come to understand something quite profound about this. The everyday world. More to the point, you'll understand something about the bits that make up the everyday world and how those bits stick together. And by everyday world, I mean not only what you can see out there, but the entire universe. And not only the universe at this moment, but right back to the beginning of time. So, it's a big job. Mainly the job of these people, particle physicists. There they are, in their natural habitat. The things they're trying to discover and understand, the particles that make up our universe, are at least as small compared to the Large Hadron Collider as the LHC is compared to our entire Milky Way galaxy. That is mind-numbingly small. So small it's incredible that we can know anything about these particles. But we do know things. Through a process of experimentation and making theoretical models, physicists discover what kinds of particles exist and how they interact. It's a journey that never stops. Discoveries revise models, and those models suggest new experiments. When you're a kid, you learn that the world is made up of atoms. An atom is a kind of particle, a basic piece of matter, and you're told to picture them as round balls. Later, you learn that there are over 100 different kinds of atoms that can be organized into a periodic table of elements. But it turns out that atoms aren't the very basic bits that make up everything. Way back when, experiments showed that there were particles called electrons inside the atom. And if electrons are one part, what is the rest of an atom? And how did those two parts fit together? Coming up with an answer to that question meant creating a model.
When you talk about building a model, it's something that physicists have been doing for hundreds of years. One observes the world, makes measurements, then tries to find a pattern in them, and a mathematical description, a picture of what's going on that can explain those results and be used to derive predictions for other scenarios that one can test.
What scientists came up with was this: a raisin bun. The raisin bits were the negative electrons, and the bun was the positive part that balanced out the negative charge of the electrons so the whole atom was neutral. Not a bad idea for what was known at the time, but you'll notice that we don't picture atoms as raisin buns these days. And you can thank this guy for that. The raisin bun model of the atom was exactly what Ernest Rutherford was testing when he devised a very clever experiment that produced one of the great breakthroughs of particle physics. Here's what he did. Rutherford started with some radioactive material that he knew emitted particles with a positive charge called alpha particles. Next, he chose a target, a very thin gold foil, and positioned this so it'd be hit by the alpha particles. Then, to detect what happened to the alpha particles after they hit the gold foil, he encircled the whole thing in a chemical screen that would create flashes when struck by the alpha particles. This is what he observed. Almost all the particles flew right through the gold foil and struck the screen on the opposite side. A small percentage were deflected a little to one side or the other. But the biggest surprise was when a very few deflected backwards, as though they hit something very hard and immovable. Now, the raisin bun model of the atom would not have predicted that last result. But what model does?
So if you take an object and you know its energy, and it's basically moving at the speed of light, and it bounces back. You can get a classical estimate for how much force that atom would have to apply. And if the length scale of that energy transfer is much, much, much smaller than the atom itself, that's where you say, aha, the atom is not some billiard ball, it's got to have some structure in there that's much smaller than the atom. That's how he arrived at his model, that there's got to be some solid core that's much smaller.
In time, the nucleus itself was shown to be made up of smaller particles called neutrons and protons. In effect, this model reduced the collection of around 100 elements to a more fundamental model of just 3 particles. It's easy to overlook just what a breakthrough Rutherford made with this experiment. Not just for what it discovered, but for the technique of colliding particles together as a way to penetrate inside the structure of matter. Before we move on, we need to get a few physics concepts straight. When charged particles interact, they don't touch the way we think of 2 pool balls touching. Instead, they interact through forces at a distance, and the way physicists picture these forces is with fields. When you throw a ball into the air, the ball is interacting with Earth's gravitational field. Its kinetic energy is being converted to potential energy by the field, and then back to kinetic energy on its way back down. How high it travels in the field depends on how much kinetic energy it started out with. In Rutherford's experiment, the alpha particle and the gold nucleus were interacting in the electric field surrounding the gold nucleus. As the alpha particle moved directly towards the gold nucleus, it began to slow in the field, its kinetic energy being converted to potential energy. It came to a stop, and that potential energy converted back to kinetic energy, and the particle flew off in the opposite direction. In a particle collision, the more kinetic energy particles start out with, the closer together the particles will get. The history of particle collider experiments is one of designing larger and larger machines to create higher and higher energy collisions in order to see deeper and deeper into matter. As particle accelerators became capable of focusing energy in such a microscopic volume of space, something quite extraordinary happened. New particles were created. I know, that may sound like magic, but at the scale of fundamental particles, the rules of physics not only allow for it, they predict that it will happen. The key rule is E equals mc squared. And what that means is that mass and energy can be converted one into the other, just like you can convert British pounds into dollars at a certain exchange rate. Only the exchange rate between energy and mass is c squared, the speed of light squared.
Mass and energy are just 2 faces of the same thing. You cannot differentiate between one versus the other one.
One way to interpret this formula is to think of mass as just a type of energy. And consequently, if you have a lot of energy, you can also create mass, or in other words, matter.
You can actually see particles popping into existence in the particle detector of an accelerator. For instance, in this image from a bubble chamber detector, the tracks were created by charged particles passing through the detector. The detector has a magnetic field, so particles curve one way or the other depending on whether they have a positive or a negative charge. Look closely at these 2 spiral tracks that appear out of nowhere and curve off in opposite directions. What you can't see is the photon, a packet of energy that was traveling through the bubble chamber when it suddenly turned into these 2 new particles. This track curving to the left is an electron, which has a negative charge. But this track curving the opposite way has a positive charge and turns out to be the antiparticle of the electron, called a positron, an antiparticle that has the same mass but the opposite charge.
And so when you collide things with lots of energy, what typically happens is that there's lots of particles there, and they will be pair-producing new kinds of particles all the time, particles and antiparticles, as long as you have enough energy to produce their mass, which is related to energy through E equals mc squared. In all these collisions, the things that are coming out were not there to start with, and so you're getting a sampling of all possible particles that could be produced at the energies that you have access to, which makes it much more efficient. You have to choose the initial thing carefully to have the right ingredients. You can collide almost anything at high enough energies, and you're going to get everything out.
So how much energy do you need to create a particle? About this much. Not much. But it's not only a matter of how much energy you create, but how much energy you can put into a very, very tiny space. In fact, when particle accelerators began operating at high enough energies, all kinds of new particles began showing up in detectors. These weren't the particles that make up the matter around us. Instead, they were massive particles that would pop into existence and then decay quickly. In a few decades, physics had gone from 3 fundamental particles found in the atom to a multitude. They called it the particle zoo, and physicists had to find a model that explained it.
So in the 50s and the 60s, particle physicists were discovering new particles at a very fast rate. And it was very unclear whether or not there was some underlying organizing principle sort of tying together all of these particles, or if each new particle was just sort of a separate entity with its own properties sort of unrelated to the rest of the particles.
When physicists develop a model, they're finding a pattern that explains what they are seeing in their experiments. In the everyday world, we're pretty good at detecting patterns, but some patterns are more complex than others. Here's what I mean. You know those music visualizers that you can find on digital music players? The ones that use information from the song you're playing to alter and transform the animation. The result is a complex animation, but rhythmic and beautiful. Now, imagine that you lived in a world of music visualizers, but you couldn't hear the music. As beautiful as it seemed, it would be difficult to understand why your world looked the way it did. But if you were the curious sort, you could, by careful observation, start to find patterns in what you see. And with some creative thinking, you could even reconstruct the underlying music. And with some clever modeling, you'd discover little things called notes, which combine in different ways to create your world. The particle zoo presented a similar problem. What was the pattern that connected these particles together? Physicists did eventually discover a pattern by arranging groups of particles according to certain characteristics. The pattern revealed that most of these particles weren't fundamental at all. They were made out of a combination of more fundamental particles called quarks. There are 6 quarks in all, 12 if you include their antiparticles. The up and down quarks are particularly important for us because they make up the protons and neutrons that we find in the everyday world. Each proton or neutron is a bundle of 3 quarks. 2 up quarks and a down quark make a proton. 2 downs and an up make a neutron. While quarks seem to solve the problem of the particle zoo, they left physicists with a new one. How do these quarks stick together in the way that they do? The answer required coming up with a new fundamental force of nature called the strong force. The strong force is a fundamental force like the electromagnetic force, but it acts very differently. A quark can have one of 3 charges, which are labeled as the colors red, green, and blue. Combine them together, and you get a color-neutral particle. And while the electromagnetic force gets weaker the farther you get from a charge, the strong force is weaker nearest the particle and actually gets stronger as you move away. Now, think about that for a moment. As long as the quarks are near each other, they're bound together loosely. But the moment they try to separate, they experience a stronger and stronger force that keeps them confined. A bit like an elastic leash that pulls back the further out you pull it. That makes it nearly impossible to separate quarks from one another. What we call a proton or a neutron is really the very, very small area where a group of quarks is confined by the strong force. That nucleus that Rutherford discovered so long ago is actually a seething mass of quarks held together by the strong force in groups of 3s, which we call protons and neutrons. And around those, held more loosely, are the clouds of electrons. But the complete model of particle physics involves more than the atom. It has to include all particles that exist in the universe. The current model of particle physics is called the Standard Model, and it describes all the fundamental particles that we know of and the forces that make them stick together. It's one of the most successful models ever. It can make predictions about particles to an amazing degree of accuracy.
If you take the particles that we know about, and you ask, what's the most general way in which those can interact at low energies, consistent with quantum mechanics and relativity, the Standard Model is it.
I'll describe it briefly so that we cover some of the particles I haven't mentioned so far. First, there are the particles that make up everyday matter: the electron, the neutrino, and the up and down quarks. Then there are what we call the second and third generation of these particles, more massive and unstable, but otherwise identical to their lighter cousins. In the Standard Model, there are also particles associated with each kind of force. These force particles, called bosons, carry the information of a particular force. For instance, the photon carries the information of the electromagnetic force, the gluon for the strong force, and the W and Z particles for another force called the weak force. So these are the particles that make up our universe and that have been detected in particle accelerators so far. Now, it's one thing to make a list of particles, but a complete physics model must describe how all these things relate to one another.
For a given model meaning a description of how the world works, there are a set of equations. And things like particles and particle interactions and forces, all of these concepts are in the equations.
So, for a physicist, the model will look something more like this. Mathematical equations that spell out how all these particles relate to one another. Now, if we look closer, we might notice a term in here. Let me find it. Here it is. An H. The H is a particle called the Higgs boson. It is the only particle in the Standard Model that has never been detected in an experiment. So why are physicists so sure that it exists? For one thing, the Standard Model doesn't work without it. Imagine you're standing on a subway and it stops suddenly. Yeah, you keep moving forward. That property of matter is called inertia. Inertia is a resistance to a change in motion, and it is caused by the property of matter called mass. In fact, objects have inertia because of their mass. Most of the mass of everyday matter comes from the energy involved in holding its fundamental particles together. E equals mc squared at work again. But fundamental particles can have a mass too, all on their own. So the Standard Model needs to explain where fundamental particles get their mass. That is where the Higgs comes in. Here's how it works. First, the Higgs boson is associated with a field, and it's the Higgs field that is the really important idea. The Higgs field fills the entire universe. It's everywhere. You can't get away from it, like a sticky fog that has settled around everything. Because it is everywhere, every particle is traveling through it, and most particles are interacting with it. When a particle moving in the field tries to accelerate, it experiences a resistance. The idea is that the particles don't have a mass on their own, but only through their interaction with the Higgs field. How much resistance the Higgs field exerts depends on the particle in question. If you're a particle like an electron, you interact with the Higgs field and experience a resistance every time you try to accelerate. On the other hand, if you're a photon, you glide right through the Higgs field without interacting. You're massless, and you go about your business at the speed of light. Remove the Higgs from the Standard Model, and it would predict that all particles would be massless particles, just like photons, which they aren't. And it's a good thing, because our world would be very different without the Higgs field.
If you look at the world around us, we know all the atoms are built out of protons and neutrons. Now, each of these protons and neutrons is itself built out of 3 quarks, but different quarks. And the Higgs field interacts with these different quarks, slightly different amounts. That actually makes the neutron a little heavier than the proton. The fact that the Higgs mechanism makes the neutron a little heavier allows you to have a stable proton, stable hydrogen. The fact that it's only a small difference lets you build up the entire periodic table of elements. So that means we can have all of the materials that this chair is built of, that the world is built of, chemistry and stars. Every process that 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 we know and love and that makes this world possible is largely due to this precise difference between the proton and neutron masses.
So, wouldn't it be great if we had some evidence that this Higgs field exists? All we need is a giant particle accelerator. Hold on. They've built one of those. Because fields are associated with porous particles called bosons, if you detect a particular boson, you have evidence of that particular field. So, if the Large Hadron Collider can detect a Higgs boson, that will be evidence that the Higgs field exists. The LHC will create interactions that involve about 10 times more energy than any accelerator that has come before.
The LHC, the way it reaches these very, very high energies, has a number of different components to it. And the first, which many people don't think about very often, is the kind of particle that's being collided. We're colliding protons, which are 2,000 times as heavy as, for example, an electron.
We accelerate protons by passing these protons through an electric field that is being generated via accelerating cavities. It's much like a surfer that gets pushed by waves in the ocean. These protons get pushed by an electric field as they pass through these accelerating cavities. And in gaining speed, they gain a lot of kinetic energy.
It's a combination of a large size and very, very strong magnets, which you use to bend these particles in a circle to keep them under control. There are these quadrupole magnets which are used to squeeze the beam down and make it as narrow as possible, make the particles as dense as possible, so that when they collide, you have those very, very high luminosities to give you the most number of collisions.
Imagine protons as fishbowls and the quarks as ice cubes tossing around inside, and they are flying towards one another at high speed. Most of the time, the bowls would just smash together. But every so often, two of the ice cubes would also collide. In the LHC, it is the rarer collisions between quarks and the gluons that hold the quarks together that will produce the really intense energy needed to create a Higgs boson. It's one thing to create a Higgs event, but you also have to be able to see it happen. No particle accelerator is complete without its detectors.
Our detector is made up of different layers of sensors. And each of these sensors is designed to measure the trajectory, the energy, and also the different types of particles that emerge from this head-on collision. We wouldn't directly see the Higgs, but rather the different types of particles coming from the disintegration of a Higgs.
And by the pattern of those particles, physicists will know a Higgs boson must have been present.
So here's the problem, though. So you have billions upon billions of particles flying into this detector every fraction of a second, okay? And you have to digitize all the information that represents their trajectories, okay? You got to digitize all that information. You got to pump it up to computers to throw out most of it, because at a raw level, you have well over terabytes per second flying up into the main processors that are actually in the collider halls. And that's got to be filtered down to a more manageable level, which you can then pump out into a computing grid to reconstruct exactly what happens in these events.
At 600 million collisions every second, there's a lot of data to sort through. And even though physicists know what kind of signatures a Higgs event will produce in the detectors, sifting through all those events to find what they're looking for will take months or years. So, if the Large Hadron Collider detects a Higgs boson, it will fill in a critical part of the standard model. And that will be pretty amazing. But the LHC is doing much more than looking for one particle. It is delving into matter at the smallest scales ever, allowing us to look into a realm of very high energies, and it is recreating conditions that haven't existed since a split second after the Big Bang. And if experience has taught us anything, it's that when you explore deeper into matter, there's a very good chance you'll discover all sorts of new things. Maybe the Higgs particle will be found, or other particles, or even new forces. And if that happens, and it's likely, then the standard model will need to be replaced by a new model.
I've been in the business for 20 years, and they've been planning the LHC for 20 years. And we've been waiting for this thing to be built, so you'd find what's going to replace the standard model, and now they're running, and now they actually already are releasing data, And in the next year or so, they will tell us about the Higgs, and it's extremely exciting to finally get experimental information about what's going to replace the Standard Model.
On what scale the LHC will be important, we don't really know yet. But what we do know is that it's answering questions that have been the driving questions of particle physics for 20 years.
What I would really love to see, and what I've been working on, is looking for substructure to quarks. So this is looking for excitations in quarks. This would be earth-shattering in the sense that it would take us to the next level. It would take us to something smaller than a quark, using techniques that were developed 100 years ago, but at much, much higher energies.
I hope that they see a candidate for dark matter, because that's one of the biggest puzzles as a cosmologist that we are facing with. Where is this? What is this mysterious matter that is dominating our universe, but we don't have a clue what it is? So let's hope there is a candidate and LHC can see it. That would be a big discovery for me.
There's the possibility that the LHC could actually uncover a part of the world that we had never seen before because it was very, very weakly coupled to us at low energies. My own gut instinct is that nature is probably much more clever than we're being right now, and will give us something surprising and interesting to work with.
I think, and I truly believe that in 20, 30, 50 years from now, in physics textbooks, we'll be talking about the pre- and post-LHC era in terms of our knowledge and description of nature.
What I'm really curious about is how science will follow up on this experiment. How deep can you explore into the little bits that make up our everyday world? And what kind of models will come out of what is discovered? I guess what I'm saying is that even this moment in science will pass, and we will move on to new discoveries, new models of the world. And that is pretty exciting.
Physics.